Okay, and Natalia, she's a physical oceanographer, and she did a PhD at the ZMT, the Center for Marine Tropical Ecology, I guess, in English, and with a focus on geomorphology, hydrodynamics, and the sediment transport. But she got really interested in ecology and biogeochemistry during her PhD at the ZMT. So she calls herself a hybrid oceanographer. And apart from science, she really likes to surf, actually. So maybe we see a picture of surfing in the end. I don't know. Okay, so there will be 20 minutes of talk and 10 minutes of discussion. And Natalia, please start.
Yeah, thank you so much, Peter, for the nice introduction. I will be talking today about the temporal and vertical distribution of nutrients in and oxygen in the Namibian shelf. This is a project embedded in the EVAR project. And so if you see my pointer, then on the top, you see a picture of the team that we were collecting data at the last Meteor cruise. That was in 2019, here in the Namibian shelf. Okay, perfect. So the structure of this presentation will be, we'll have a quick overview of the Bengala upwelling system, even though you are surely familiar with this system. It's worth to mention a couple of things. We also will be talking about the ecological implications of upwelling, the physical mechanisms that drive oxygen concentration, and I will show some results from the last cruise, but also from numerical experiments with the output of our model. So this region is very complex when we talk about the oceanography, but we can kind of simplify it by mentioning two central water masses that make a big influence into the biogeochemical processes that we find in this area, and also the chemical composition. So the first water mass, the one you see here in this map, is the South Atlantic Central Water in red. It originated on the equatorial. It's a quite old water mass that has a very long residence time in the trapped in the Angola Gyre, and the oxygen gets depleted in that time. Contrary to it, we have the East-South Atlantic Central Water flowing upwards, depicted in blue. And this is a relatively young water mass that is oxygen-rich, but relatively poor in nutrients. So the interaction of these two central water masses give the Bengala upwelling system very interesting setting, in which when we have very intensive upwelling events, there is a generation of mesoscale filaments that bring up the nutrients, and we have these phytoplanktonic blooms that we expect on an upwelling system. Because it's very productive, this carbon produced, the biomass produced is not always consumed, and it sinks to the bottom. In this area, we have sediment formation that is very particular for that region. We call it the mud belt. It's a very organic rich sediment that goes all parallel to the coast. Here we can see some pictures of the bottom. In the first picture shows the typical anoxic sediments we found in this region. In the photograph, you can see some little dots, and this is most likely marine snow and high turbidity that sinks to the bottom. In contraposition, the oxygen sediment is more stable, and it doesn't show this fluffy feeling to it. It's more consolidated. Well, it was about the spatial distribution in this region, but what about the vertical overview. Well, the first thing I would like to highlight is that when we talk about the biogeochemistry, we mean the chemical composition of the water column, that it's distributed in that way, or it's explained by different physical processes and drivers, like, for example, wind. When it beats the surface of the ocean, it enhances the mixing of CO2, for example, and it dissolves in the water column. So there are physical and biological drivers, for example, and this is what we call biophysical interactions, right? So we have this CO2 that is mixed into the surface, and then the biological pump, or following the carbon cycle, the phytoplankton will assimilate the CO2 with different nutrients, create this organic material we were talking about. And what is interesting here is that this organic material, we estimate that about 10% of it is not consumed, and it will sink into the bottom. When we move down to the aphotic zone, this organic material is also the main source of energy for the ecosystem. But to break apart and get the remineralization going on, we need quite an amount of oxygen for it. So the system is demanding a lot of oxygen if there is a lot of organic material on the water column. This can produce a particular situation, which is called, well, the formation of an oxygen minimum zone. And this will produce some anoxic conditions. In these anoxic conditions, we have other processes that play a major role in there. I will just mention that in Namibia, the occurrence of large sulfur bacteria like Theomargarita namibiensis is very well known because it's pretty unique. And this bacteria, what it does, it takes the H2S that is formed on the sediment by the reduction of this organic material and the different components. And this subproduct is very toxic. And what Theomargarita does is to take it as an energy source and release sulfate, that it's again available for the system. It's important to mention that if the system falls in one of these situations, very stagnant situation, it might need an impulse or an external force to break it from that situation. It's not that the system is unbalanced, it's just another state of the system. So let's have a look to the oxygen distribution. And now we can talk about a scenario in ocean warming. What changed, what influenced this oxygen inventory? Well, this is just a very quick overview. And so in general, the solubility will decrease, which also will make that the oxygen concentration will decrease. It is estimated at about increase of 5% of 5 degrees temperature can shift really the phytoplankton from autotrophic to heterotrophic, and this of course could reduce the oxygen concentration. And here we are probably more interested on the stratification. If we have a higher stratification, high stratified waters, the ventilation will also reduce, which means that this mixing and exchange of water will reduce, and overall will reduce also the oxygen concentration and the oxygen transport. So some ventilation related mechanisms for the vertical profiles. I would like to mention two main mechanisms. One, it's called oxygen subduction, and it's basically when the flux of oxygen from the upper surface waters flux into the permanent thermocline, which makes an increase, it triggers the increase of oxygen concentration in the ocean interior. And this, we also would say that it increased the oxygen inventory. The opposite phenomenon would be, it's called abduction, and this is the flux of oxygen into the mixed layer, the surface layer. These water layer, these layers have a distinct biogeochemistry and therefore also physical properties. I'm not going into the detail to that. Here's some results from our last campaign in September 2017. We were collecting samples from 3 different transects. One to the north, very close, well, a bit southern from the Kunenzel, showed very, oxygen depleted waters, which it's not surprised because the composition of this water mass, this water composition fits to the water current coming from the north, which was oxygen depleted, as shown in the introduction. The transects on the 23 and 25 show also more stratified conditions. We see higher dissolved oxygen in the surface layers, and it decreases close to the bottom. So same for the turbidity, and we see more turbid conditions close to the coast, but also close to the sediment. Let's have a look to how dynamic this water is. This is the turbulent kinetic energy in the first panel, in the first column, and the eddy diffusivity on the right column. And now I'm just focusing the lower 2 transects, the 23 and 25 degrees south. In the 23 degrees south, we see a higher kinetic energy in the surface, as we expect effect from the wind, and close to the sediment, which gives the idea that the sediment is being reworked, and there is some interaction from maybe intermediate currents or internal waves. The same happened to what we see in the transect 25. We particularly see here enhanced vertical mixing, which we think it might be because the effect of internal waves. So now let's have a look to the time series analysis we did with the output of our model. In general, this panel shows the raw data in the upper panel. We extract the seasonal patterns from that raw data. We have here a zoom in from that seasonal pattern computed in there, where we see the maximum oxygen concentrations during September and October. This is not an absolute trend line, but relative, and it seems I'm not showing the total trend, but in general it seems that dissolved oxygen is increasing in this time span. I'm just showing from 2005 to 2017, even though we have a larger computational time, because in the first years we have some spin-up time, and I just took the central the central data to make sure that it's not affected by spin-up or the initial conditions, for example. The remainder will be just the residuals from the trend and the seasonal fit to the raw data. Once again, here on the corner, we see how what the oxygen demand is in this area, and it's pretty high, particularly close to the sediment. In the introduction, I was saying that to decompose this organic material, we need a lot of oxygen, and this is what might happen here because we have very organic rich sediment. Here in the seasonal analysis, we see that well, the nutrient maximum we see it around October or so. And what is interesting here is that when we see the trend, it seems that it's decreasing. So we have like two different mechanisms that can affect that too. So we have a very interesting situation here. We have like oxygen might be increasing. Perhaps it's because the oxygen organic matter decomposition, and that will lead to a increased nitrate concentration. But of course, we don't know about that. It's just speculation at this point, because it could also be driven by other physical mechanisms like ventilation that increase oxygen, and it doesn't necessarily need to increase nitrate. However, when we have a look to the detritus or organic matter, it seems pretty stable through time, slightly decreasing, but probably that's not significant. So, yeah. Yeah, so in general, we see here, and this is just the analysis for a particular location here.
3 minutes.
That's perfect. I'm about to finish already. So yeah, these results are preliminary results at this point. We are still doing some analysis on that. Just to show, because I thought that there might be some biologists interested on this talk. This is also the output of our model, and it shows that there is no really increase or decrease on large phytoplankton or small phytoplankton, slightly decrease of the small phytoplankton cell. Components to it. Well, the main take-home message I wanted to share today is that we have the distribution of two central water masses, the east-south. And these two water masses really give a predetermined situation for the system. Also, we see that the oxygen demand from the sediments is pretty high. And some preliminary and interesting results that perhaps the local oxygen inventory is increasing because of physical mechanisms or biological mechanisms. This is something that we're still figuring out. But that's it for my side. Thank you so much.
Okay, great. Thanks a lot, Natalia.
Go ahead.
The first question comes from someone who is always hearing talks about the Weller upwelling system. And the oxygen minimum zone, is it like a natural thing, or did it change on geological time scales? Is it kind of influenced by humans or so?
I mean, that's actually a very good question. And I'm not a geologist, really going that far back in time, but definitely something that occurs frequently and recurrently. It has a seasonal pattern. And yeah, if it's intensifying or is getting weaker or not, this is an open question at the moment. What doesn't mean that, it doesn't mean that the system is unbalanced. It's just a process that happens, and particularly when we have very large phytoplanktonic blooms, it could be influenced by anthropogenic impacts, for example, of fisheries. If there is not enough heterotrophs that are feeding on these autotrophs or in that biomass produced in the system, this could definitely increase the organic materia, the volume of organic materia that is not utilized.
Okay. Kurt, yeah?
Yeah, Natalia, thank you. I learned a lot again, but you also introduced terms that I have heard for the first time, like subduction of oxygen and obduction of oxygen. Now, I understand subduction is the bringing oxygen into the deeper waters. Is that correct?
That's correct, yeah.
And where does that originate? Must be from the surface.
I mean, yeah, it could be like, for example, we are close to the shore, and breaking waters or breaking waves also push these oxygen fluxes down. I mean, it can have like many different, can be originated in many different ways. What it's maybe relevant for this talk is that we see the opposite happening in, maybe I forgot to mention that.
You know, what surprises me is that you have oxygen going down at all in an upwelling system. Okay.
Yeah, because we are in an upwelling system, but
Right.
so here in this system, predominantly we will have from bottom to the up flux. That's correct, and we see it here. For example, we see here some kind of patch of dissolved oxygen going to the top here too. So yeah, definitely in this system, this would be the main mechanism. Yeah.
Now, well, this is something we should discuss further anyway, but let me point out another thing from the same figure that you just showed. You mentioned also solubility of oxygen is not a key parameter in the long term. It's the respiration. Right? So that's a consumption of oxygen that has probably globally the biggest impact. But look at the top graph at point T2, just what you had before.
Oh, okay.
That's what slide number 9. Yeah. Slide number 9.
Oh, sorry, yeah.
Yeah, here, okay. Look at T2, that's the top graph with regard to oxygen. There you have much less oxygen than on the other two transects. And this is due probably to the warm Angola's waters that come down and then get out into the ocean. So oxygen temperature or water temperature certainly does have an influence on solubility. That's a physical aspect. And why do you think further down it does not make so much difference?
Well, what we are seeing here probably it's pretty much pure subtropical water flowing down. It's very oxygen depleted, and if we have a look here vertically, the water is much more homogeneous, whereas farther down we might have more a mix of these two water masses interacting, and this brings us in also a more dynamic situation. So that's unfortunately I don't have here a graph that shows the percentage of the water that belongs to the South Atlantic Central Water and the Eastern South Atlantic Central Water, but that would be a interesting graph to mention and show next time probably. Yeah.
And you might also consider, besides respiration and solubility, production. Further south, where you have the
production, yeah, that was kind of an introductory way, an introduction to actually talk about ventilation. Yeah, but yeah, thank you for pointing that out.
Yeah, I'm unmuted. Yes, hi, Natalia. Thanks for the nice talk. I have like a question regarding like that interesting observation that you said is like maybe a bit preliminary. I don't know that you saw like kind of like more oxygen in since 2012. Is that correct?
Yeah, that's right.
Do you think, I don't know where you are with that, but do you think it could be, or like kind of like from what I remember, like working in the Benguela and like with the in the Genus project kind of a couple of years ago, obviously. They were like, and like from Volker Moorholz's et al. Work that kind of like you have like these discussions, how much influence on the oxygen or lower oxygen values we measure comes from the different water masses, and how much comes from like decay processes, kind of like biological production decaying, and then bacteria playing a role. And then I remember that like we also discussed like the effect of like other vertical migration of like plankton and other organisms that could contribute to like depletion of oxygen in like lower layers, like a bit farther out in the shelf. So I don't know if that is like something that you think is like relevant at all, but I would be curious what your take is on that kind of like theory, and like what do you think? Do you have any kind of like what do you think is most likely that is behind like the observation you have there in the model?
Yeah, I mean, showing this was a bit provocative because in general we talk about ocean deoxygenation, the opposite phenomenon, and yeah, definitely we should, to avoid some model misinterpretation, we should integrate for a larger zone, and these results are also integrated through the whole water column. So, I mean, at this point, it seems that also the Tridus somehow is slightly decreasing. I mean, if I have to, go a bit farther on that, it seems that it's pointing out to that the decrease of the Tridus, that maybe utilize less oxygen. But it's very, at this point, is preliminary results, and just wanted to
sure.
Show it in general. A further analysis in more detail, take into account the different range of water depths, and also a larger region would be more,
And like you showed, like the phytoplankton was like, I mean, at least like for me, it didn't look like anything changed there. Do you have like any data about like zooplankton or fish? Did that change? Or like maybe anybody on the call here?
This is all model output, so I don't have this data. It would be very interesting to compare to observational data in any case.
Is the model stable? I mean, can you wiggle around with the parameters and it still shows the same, or is it you change X and then suddenly oxygen decreases also?
I mean, it's a very large ecosystem model. We don't change parameter that lightly, but we did change some boundary conditions, and yeah, the model is pretty stable. So, as I mentioned, it needs a couple of years of spin-up time, and after that, it seems to reproduce very well the system.
I think Dion also wants to say something.
Yeah, I just want to ask, the model, is it based on the surface or at sediment level or at the bottom? I was not totally. It seems when the phytoplankton, can you just quickly go to the phytoplankton slide for me?
Yeah. That one? Yeah.
Yeah, this one. Which shows that in the first quarter or first half of the year, that phytoplankton is, and this during the upwelling period, which is around April, September, October, it's higher.
Yeah.
That's correct.
Sorry, I missed you a couple of times, and if you can repeat your question.
Yeah, my internet is very slow, and yes, I also hear you not very good. I asked if this is the model output. It shows that in the first half of the year, phytoplankton is low, and then in the second part, phytoplankton is high. which is sort of contradictory to the in situ phytoplankton data that I have, and I will present that on the 12th. And Anya will also present some oxygen data, I think next week, if I'm not mistaken. And it shows, as I said, even the oxygen is sort of, yeah, it's lower, if I correct, remember your slide. In the first half of the year, it's
well,
low.
In January, it starts from a peak. So the first January and February, it starts with a relative high amount. It drops afterwards, and it increases definitely in September and October. This is also the mean value computed for many years. Also from our data collected during September 2019, of course, it doesn't totally fit these mean values because it has been computed for many different years and with a high variability too. But in general, the pattern shows at the beginning, January and February, starting a bit higher, dropping, and then increasing in October, September.
I just was going to ask, how much, if it's known, how much do you think the oxidation of sulfide and methane that's flexing from the sediments contributes to the overall oxygen consumption in the water column?
We don't know at the moment, but this is definitely something that we will investigate.
Great, thank you.
Sorry.